So we've talked about a matrix multiplication as a generalization of multiplication of real numbers. And if that's the case, then we should have something that is going to be the generalization of division by real numbers. In fact, the matrices that satisfy the conditions of the previous theorem are very special. They are invertible, and these are exactly the type of matrices that we can hope to divide by. Now, I need you to understand we're not really dividing by a number, but invertible matrices have, roughly speaking, that same property that the real numbers that are not zero have, right? With a real number that is not zero, you can invert it, right? If x is not zero, 1 over x is a real number, and it's like the inverse of the other one. So we're going to see how we could build a notion of invertibility for square matrices, and it's important they have to be square matrices, and that these matrices will have properties that are, roughly speaking, what we have in mind when we think of a number being invertible, but for matrices. So if you're looking at a special case of one system of linear equations in one variable, then the matrix equation ax equals b is in fact, the scalar equation little ax equals b, right? The kind of stuff you remember from high school. Now, if you view this as a linear system, you're either going to have no solution, like no solution at all. When does that happen? You'll have no solution when this thing is degenerate, which is to say on the left is 0, and on the right you don't have 0. Well, for this to happen, you have to have an a, which is 0, and a little b, which is not 0. Or you'll have a unique solution if it turns out that, well, a is not equal to 0, in which case you can actually solve the system by dividing b by a. And then you'll have infinitely many solutions, and all of them will look like x equals t, where t is some parameter, if it turns out that both a and b are 0, so degenerate but actually consistent, as opposed to the first case, which was degenerate but inconsistent, which I didn't actually specify the inconsistent stuff. So we want to come up with a way to basically divide here by this vector b. We want to divide the vector b by a matrix A, right? Which is basically what we're trying to do when we solve here and get a unique solution. We're dividing the constant vector, which just happens to be in 1 by 1 vector, so a real number, divided by the coefficient matrix A, which just happens to be a 1 by 1 coefficient matrix, so a real number. Can we do something like this for the general case? Because if that's the case, then we could write that the solution of the system ax equals b would simply be b divided by the matrix A, or whatever that might mean. It turns out that there's a natural way to view this that will allow you to actually do something like this. So instead of writing x as b divided by a, we're going to rewrite it. We're going to reword it so that division by a will be the same thing as multiplication by the inverse of a. And we know that that makes sense because with real numbers, if I'm dividing by 2, that's the same thing as multiplying by the inverse of 2, which is the same thing as multiplying by 1 over 2. That's sort of this trick that we had. So we do the same thing here. Instead of dividing by a, we are multiplying by the inverse of a. Now what we're trying to do is to say, well, what would that thing actually represent if we had a inverse? What could it mean? Now, if we know that, then it'll be easy, because then the system ax equals b, assuming that it is consistent and that it has a unique solution, its solution is only or simply going to be A inverse times B. But for that to make sense, in order for this to make sense, you at least need the dimensions to be compatible. So if B is an n by 1 vector, you at the very least need to have n columns for this A inverse object. Otherwise, you have if you have something else, right? If that something else is not equal to n, you will not be able to get a matrix product which is defined. So that's one thing. On the other side of the equation, we think that this should give the solution vector x. Now, this solution vector x is going to be n by 1 as well, right? Because it has n unknowns. We have a system of n equations and n unknowns. So in order for x to be n by 1, you need this here to be n by 1, which means that this number also has to be n. So whatever the inverse is going to be, at the very least, we know that if A is n by n, A inverse should also be n by n. Okay, so that's something we wouldn't necessarily have known, but it's imposed on the situation if we want the inverse to behave like division by a real number, which is not 0 in the case of an 1 by 1 system. But what's the defining property of the inverse? With real numbers, that property is that if A is invertible and you multiply it by its inverse, you should get 1. You should get the unity object with respect to multiplication. That's also going to be the case for matrices. But you have to think of which matrix would play the role of that 1. It turns out that the n by n identity matrix IN will have the required property, right? It behaves like the real number 1 does with respect to matrix multiplication. If B and C have the right dimensions, then B times IN is just B. And IN times C is just C as well. This is what the property of 1 is for real numbers. 1 times anything doesn't, have any effect. With matrices, though, we have to have it on both sides, right? Remember, because matrix multiplication is not commutative. The order of multiplication matters. Okay, so from a matrix perspective, then, if you have two square n by n matrices, A and B, that are such that A times B is equal to the identity, and that B times A is equal to the identity. The fact that they're both equal to the identity imposes a condition that doesn't typically occur, right? A times B is not usually equal to B times A, but if both of these things are equal to the identity, then they have to be equal. In that case, you would say that B is the inverse of A, and you would write B as A inverse, A to the minus 1. At the same time, if B is the inverse of A, then A is the inverse of B. And then you could write that A is equal to B inverse. But because B is equal to A inverse, what you would get is that A inverse inverse is A. So inverting a matrix twice sends you back to the original matrix. If that's the case, both A and B are invertible. So an invertible matrix is a square matrix for which there's some other matrix that you can multiply it by to get the identity matrix. And one thing we can show is that the inverse of the identity matrix exists, and hence the identity matrix is invertible. In fact, the inverse of the identity is actually just itself. That's not usually going to happen, but this is one instance where that is the case. How do I know that? Well, if I multiply I by its suspected inverse, I do get the identity, because the identity times anything just gives me the anything. Okay, so the identity matrix is invertible and its inverse is itself. What about the following matrices? If I look at A, which is 1, 1, 1, 2, 3, and B, which is 3, minus 1, minus 2, 1. Then I do the product. A times B. Remember how it works? The matrix on the left gets the rows, the matrix on the right gets the column. So 1 times 3, which is 3, plus 1 times minus 2, minus 2, 3 minus 2, 1. Then I do the same thing for the first row, second column. 1 times minus 1, plus 1 times 1, 0. 2 times 3, plus 3 times minus 2. They're the same, 0. And then finally, 2 times minus 1, plus 3 times 1, that gives me 1. Sure enough, A and B are invertible. Now, we haven't yet proved that this has to be also equal to the identity. Like, we're saying that if that's the case, then they're invertible. In fact, you don't really need both of those. As soon as one of them is the identity, then they're both the identity, the product. I mean, the order doesn't matter. But since we don't yet know that this is the case, we should actually take the time to verify it. So instead of multiplying A with B, we're going to multiply B with A. And remember here, the rows on the left, column on the right. If you go through this exercise, you will once again get the identity matrix. So what that means is that A and B are invertible and they're inverses of one another. The inverse of 1, 1, 2, 3 would be 3 minus 1 minus 2, 1. So it's easy to verify if something is an inverse of something else, but how do we actually find it? That's harder to do. In the 2 by 2 case, there's a nice formula. If you have a matrix A, B, C, D, then as long as AD minus BC is not equal to 0, then you can divide by it, and the inverse, a to the minus 1, would be 1 divided by this quantity, which you'll recognize as the determinant of the 2 by 2 matrix, right? A times D minus B times C. As long as the determinant is not 0, here we have 1 over the determinant. And what's the rest of the matrix? I said if you had an n by n matrix, its inverse is also n by n. So a 2 by 2 matrix must have an inverse which is also 2 by 2. You switch the positions of A and D. This is what happens here. And then you multiply the elements on the counter diagonal by minus 1. All right, so this is a formula that you probably need to remember by heart. I don't want to say that I'm ashamed to say that, but it took me a number of years before I remembered this by heart. Later on, we're going to see a way where we can derive the inverse without having to remember matrices, formulas. But I could never remember. I always use that little method to derive the inverse instead of just remembering this. Now, in retrospect, this isn't that hard to remember, and it would be a good idea for you to remember it. Okay, if it turns out that the determinant was equal to 0, I can't divide here. Well, in that case, the matrix is not invertible. For matrices, the condition that determines if they're invertible or not is actually a condition on a determinant. As a real number, x, or a, or whatever you want to call it, we say that a is invertible if it's not equal to 0, because then you'd get 1 over a. Well, the thing with a is that if you think of a as a 1 by 1 matrix, a is the determinant of that matrix. So even in this case here, where you can divide by a only when a is not 0, what you're really saying is that you can divide by a when the determinant of a is not equal to 0. And that's going to be the critical condition. If the determinant of a matrix is 0, that matrix is not invertible. If the determinant is not 0, then it is invertible. How do we prove that this is the inverse? Well, let's say that we call this B here, and let's assume that AD minus BC is not equal to 0. Then what I'm going to suggest you do is that you take the A that is here, multiply with the B that is here, using the rules of matrix multiplication explicitly, and then you'll get that, yeah, sure enough, the product of these two matrices, no matter the order in which you multiply them, gives you the identity matrix. So the inverse of A is indeed this thing. Now that's the easy part of the proof. To show that you cannot get an inverse requires more work. I'm not going to do it here. It's left as an exercise. But we'll take it for granted that when a matrix has a determinant which is 0, the matrix cannot be inverted. Right? Showing that something is so is easier, especially when you have a candidate, than to show that something does not exist. It can still be done, but we're not going to do it in this course. Now, without using any lemmas, which is to say, like without using conditions on the determinant and what have you, how would you show that this specific matrix is not invertible? That's going to give you an idea as to how you would prove the statement, the second half of the statement. You could, for instance, suppose that there was an inverse. Let's say that ABCD was the inverse. Then multiplying A and B together should give you the identity matrix. So, okay, sure. What is the product of these two matrices? A plus C, right? B plus D, yeah. Then I have A plus C, yeah. Then I have B plus D. All right, so this matrix here should be the identity matrix if A was invertible. That would mean on the one hand that 1 is equal to A plus C, because this is what it means for these two matrices to be equal. But it would also mean that 0 is equal to A plus C. So you would have to have that A plus C is 0 and that A plus C is 1. Right? Both of these things cannot happen at the same time. It's either 0 or it's 1 or it's neither. But it can both be 0 and 1. So they cannot be an inverse. Another way to look at the same problem, say, okay, let's look at a specific vector x, which is the vector 1 minus 1. I'm going to multiply A by x. When I multiply A by x, I get 1 times 1 plus 1 times minus 1, which is 0. 1 times 1 plus 1 times minus 1, also 0. That gives me the 0 vector. Obviously, if you don't remember how to do matrix multiplication here, you're going to be SOL. So you need to remember how to do that. Well, what does that give us? If A inverse existed, then you could multiply the equation that we got, the equation AX equals 0. And here, remember, x is a specific vector, not something that we're trying to find. You could multiply it on the left by A inverse, and on the right by A inverse. But when I say multiply it on the left and multiply on the right, you have to be careful. I'm not talking about multiplying on the left-hand side and multiplying on the right-hand side. I'm talking about taking the full equation and multiplying both the left-hand side and the right-hand side on the left. Because here, in general, if you have that, I don't know, x is equal to y, you can't say that ax is equal to ya, right? If you multiply on the left, you also have to multiply on the left here. I mean, even there, like the dimensions might not be compatible, but it's important that you multiply on the same side for both sides of the equations. That's because matrix multiplication is not commutative. At any rate, ax is equal to 0. We multiply on the left for both sides of that equation. We multiply by A inverse, and that would give us A inverse times A times x, which should be equal to A inverse times 0. On the left, A inverse times A, by definition, that is going to be the identity matrix. So on the left, we have I2 times X, and that just gives you X. So this sort of disappears, and I just have an X. And on the right, I have A inverse times the 0 vector. And anything times the 0 vector gives me the 0 vector. So out of this, I get that X is equal to 0. But I know that's not the case, because X was equal to 1 minus 1. All right, so then the only assumption I made here at any point in the argument was that A inverse existed. So that can't be right. A inverse cannot exist. So A is not invertible. Let's say we have now a matrix n by n which is invertible. Any linear system that you can write as AX equals B, and here we're back to treating X as a vector of unknowns, B is a vector of constant terms. Any such system, assuming that the matrix A is invertible, is automatically consistent. So there's at least one solution. And in fact, the solution is unique. There's only one. And it's given by A inverse times B. So if the coefficient matrix is invertible, you automatically know the nature of the solution. It's unique, and you know how to find it. You compute the inverse and you multiply on the left by B. You multiply B on the left by A inverse. I apologize. How do we prove that? That's pretty straightforward. To show that it is the solution, just say like, okay, well, if this is a solution, I should be able to multiply it by A on the left and get the constant vector B. So here's A, my coefficient matrix, times the suspected solution. Now, because of matrix product properties, which is associative, the order in which you multiply matrices doesn't matter. Well, when I say the order, I don't mean whether you do like A times B or B times A. I mean, if you have A times B times C, you can do A times B times C, that's one order, or A times BC, that's another order. In mathematics, we often use the same terms to represent slightly different concepts, and it's got to be clear from the context which one we mean, right? So A times A inverse, that's the identity matrix, multiplies B, the identity times B is B. So sure enough, this thing here is a solution to the system. What's been suggested here is going to solve the system. So we know that the system is consistent. There's at least one solution. How do we show that there can only be one? Well, let's say we have any other solution. Then let's call it y. A times y would also be equal to b, right? Okay, so now we're going to multiply that new equation on the left by A inverse. And that's going to give us A inverse times A times y, which is equal to A inverse times b. So what we get out of this, because A inverse times A is the identity matrix, we get y is equal to A inverse times b. But that's exactly the same thing as x. So if y is a solution, it has to be exactly x. There's no other choice. So every solution is the same solution, hence the solution is unique. So there's tons of properties for the inverse and how they behave with respect to multiplication. So as I've mentioned, the inverse of the inverse is the matrix back. If you raise a matrix to the pth power, like say you cube it and you compute the inverse, that's exactly the same thing as first computing the inverse and raising it to the third power, pth power in this case. you're noticing something. Like that's looking an awful lot like saying 1 over 1 over a is the same thing as a. And this is saying the same thing as e to the 1 over a to the 3 is the same thing as 1 over a to the 3, say, or p, or whatever you want. A lot of these properties are very much the same as properties of real numbers. It's just they apply to matrices in general. Not so for the transpose here, right? A transpose inverse and A inverse transpose, these would be the same. So if you want to compute the inverse of a transpose, you can just compute the inverse of the original and transpose it. That's also true of real numbers if you think of them as 1 by 1 matrices, but in that case, they would say a very silly A inverse is equal to A inverse. It's like, that's true, but like, why are you telling me? Multiplication by a scalar behaves exactly as what you think it would behave like. And that's the equivalent with real numbers of saying that k times A inverse, or 1 over k times A, would be the same thing as 1 over k times 1 over A, which is the same thing as k inverse times A inverse. If A is an actual matrix, this is what it looks like. Like if they're both scalars, it's the same thing. If they're both matrices, then the inverse of A times C is in fact, and this is the one property that is different, the inverse of A times C is going to be the inverse of C first times the inverse of A. The order here is important. It's not unlike that rule we saw for the transpose of a product. Same sort of rule applies for the inverse of a matrix. I'm not going to prove this. There's a partial proof here. The rest of it is left as an exercise. The important thing, though, is that these properties, algebraic properties of inverses, are nice with respect to multiplication. So if I look at A transpose B inverse times A transpose, can I simplify this to some extent? Sure, I can. I use the property that says that the inverse of a product is the inverted or reversed product of the inverses. So this would be B inverse times the inverse of A transpose. So I get B inverse times A transpose inverse times A transposed. And the inverse of A transposed would be the transpose of A inverse. Now another thing, it says like, I don't really want to change it around this way. Like it's true that the inverse of A transpose is A inverse transpose, but look, what I have is a product of 3 matrices. B inverse is a matrix, A transpose inverse is a matrix, and A transpose is a matrix as well. And matrix multiplication is associative. So whether I multiply the first 2 together first and then the third one after, or the first one and then the other 2 together after, I get the same answer. So let me do that. Let me multiply A transpose inverse and A transpose. Well, what's the product of these 2 matrices? One is the inverse of the other one. And so automatically, they cancel, or they annihilate, or they go to the identity matrix, and B times the identity is itself. B inverse times the identity is just B inverse. So you can simplify this to some extent. You can be careful and use the properties property. But look at this other one, which you'd like to be able to simplify. The inverse of A plus B, there's actually nothing you can do in general. If you know specifically what A and B are, you might be able to solve it. There's no easy way to invert A plus B in general. You need to find out what it is.